Hi, in this video, we will continue to look into the implementations of attributed grammars. We have a look into the introductions of attributed grammar in the previous video. So we want to know how are we going to implement the attributed grammar. So before that, let us recap a bit about attributed grammar. So what is attributed grammar? Attributed grammar actually is a context-free grammar, a normal grammar that we have learned in the previous video, but with additions of attribute and attribute evaluation rules. So means that the context-free grammar, we add two more information, which is attribute and also attribute evaluation rules. Okay, so attribute evaluation rules actually known as also called semantic function. Okay, so the semantic function is actually used to indicate to identify the purpose of the programming code that we have written. Okay, so normally for the grammar, we only look into the syntax. We just don't want to know, we cannot actually identify what is the purpose of that code. We want to know the structure is correct only. But with this attributed grammar, we can know exactly what will be the output of the code. What is the particular code used for exactly, to calculate what, for example, okay, to display what, for example. Okay, that is attributed grammar, means that you need to add the informations on the variables, the numbers, maybe strings, maybe to know exactly what would be the output of the program code. So there are two types of attributed grammar, which is synthesized attribute as well as inherited attribute. Okay, so this is examples of a synthesized attribute. Okay, so this grammar G19. So that indicate there, if you can look into this example, expression P, there is a subscript P down there. Okay, that is what we call as attribute. Okay, let me circle this. Okay, this P, and then this Q, and then this is R. This is what we call as attribute for that grammar. Okay, because we know that from this grammar we have expression goes to plus expressions. So we didn't know what will be the exact output of this grammar. So we add the attribute. Okay, and then if you look into the right part of the grammar here, okay, this is what we call as attribute rules. Okay, attribute rules is used to indicate the operations that we want to conduct onto the attribute that we have assigned for each of the non-terminal that we have there. Okay, so what we want to do with the P, what we want to do with the Q, and what we want to do with the R. So in this case, if we look into the first one, for P, Q, and R, we want to do additions of Q plus R and assign the result into P. Okay, if you look into that example. So that is what we call as synthesized. Synthesized means you have a value, you get a value of Q, which is the subclass of your derivation tree, and a value of R, also a subclass of the derivation tree from P, and the value, the addition value, you assign it to P. So in this case, P would be on the higher part or higher level from Q and R. Okay, so means that it gets a value from its lower derivation tree. Okay, so if you look into this attributed derivation tree down here, we have a plus, minus. We want actually to be able to do these operations: plus, multiple, 3, 4, plus 5, 6. So we have a constant 3 and 4. Constant 3 and 4. What we want to do is to do a multiplications. So we multiply a 3 and 4, the result becomes 12. So this is what we call as synthesized attribute. Means that you get the value from the leaf of the subclass, and the total is you return the total, the information, you return it back to the upper class. So that is synthesized attribute. Another one is inherited. Okay, if you look into the synthesized, means that you are given the return the value. Okay, you return the value to the upper class. Inherited is the other way around, means that you actually pass the value, okay, from one object to another object. You are passing the value. Okay, so inside the inherited here, we can see that they declare a type set. So this grammar is to use to a derivation for integer type, to declare integer type. Okay, so we have integer a, b, c, where we have a var a, var b, and var c. So actually we want to know what would be the data type for this var a, var b, and var c. So how we going to know? Actually the data type is inherited from this var list. Okay, so var1 actually is integer. Okay, and this var list integer get the value integer from this type. Okay, so this is what we call as a sibling relationship, because type and var list is on the same level of hierarchy. So we call that a sibling relationship. We inherit it from our sibling, previous sibling. So if you can look into the first row here, the first rows here, so the W actually, W here, we get the information actually is assigned from T. So it actually W is the same as T. Okay, W and T actually is the same because you assign T to W. Now W will have integer as well. Okay, so that what we call is inherited, because we get the value from the sibling, because you get the value from the variable object before the var list. So that is inherited. You inherit. Okay, inherit also can go in a hierarchical way. Okay, hierarchical means that from var1 here, they get the list integer here. Actually, they get the integer data types from var list, from this area. So this is what we call as hierarchical relationship. So inherited can be in the form of hierarchical, also can be in the form of sibling. Sibling means the same level of hierarchy. Now we want to see how we implement attributed grammar with a recursive descent. So the recursive descent is a coding in forms of Java. In this subject we use Java language. So how actually we want to code this attributed grammar. So to implement an attributed grammar with recursive descent, the attribute will be implemented as parameter. Okay, so attribute that we declare, the P, Q, R, S, for example. Okay, attribute. If you look into the previous example, I have put the attribute as a subscript form. Okay, attribute is represented as a subscript form. Okay, so attribute would be treated as a parameter or an instance variable in the method defining the non-terminal. For example, I have declared a grammar as AB. Okay, so assume this AB is an attribute. Attribute should be in the form of subscript. Okay, in this case I didn't write it. I didn't change it into subscript. So AB must be in the form of subscript. Okay. So as AB, S is a non-terminal, AB is attribute. Okay, is attribute. So then the method as, okay, if you still remember, so any non-terminal will be implemented as a method in a recursive descent. Okay, so the method as will have the method as will have two parameters, A and B. So how to do that? When you declare your code, you will write method S in a bracket, data type S, and and data type B. So data type, it depends on the program. Sometimes it is object, sometimes it is integer, it can be float, it can be any data type. So it depends on the problems you want to solve. Okay, so this is how you represent attribute in the recursive descent. So attribute is represented as a parameter, okay, or instance variable. Okay, remember we talked about the synthesized attribute. Okay, so it is used actually to return an informations. Okay, let's say you have add a and b just now. Okay, or a q and s, p and s, p plus r. Then the result will be sent to q, for example. Okay, then okay, write it down. Let's say I have B goes to Q plus R. So means that I have two informations on Q and R. The addition, the total value, I will assign it to P. So this is synthesized. So this means returning the informations. Okay. As I said, it is sometimes can be in the forms of object. Okay, this data type sometimes can be in the forms of object reference. Okay, or it can be a primitive. Primitive means the integer, float, double, but sometimes it can be in the forms of object. Okay, that we create in our code. All right. Okay, so this is the example. Okay, let's say I create attribute to store whole number. Okay, this is example. So when I want to store a whole number, I create an object of that number, so I can reuse it. Okay, so how to create an object? So in Java, we have several steps to create an object. Just a normal way you create an object in Java. So the step is you create a class, give a class name. Then you declare a variable. So in this case, it's about a number, a whole number. So they declare integer value. Okay. Then you have to create a constructor. Okay. When you create a class, you need to create a constructor. So in this case, I have two constructors. One is the constructor with a parameter, and one is the initialization. Okay, default constructor. Then I create get method, set method, and also a print method. So this is a normal step for creating a class. Okay, an object for a class. Okay, so this object can be used to store a whole number. Okay, now we look into the recursive descent for the attributed grammar. Okay, let's say we have an attributed grammar. Okay, S goes to A, B. Okay, so this A is a non-terminal, is a terminal, another A is a non-terminal, B is another non-terminal. So what would be the attribute here? Attribute is P, and I have R as attribute, and also S as an attribute. Okay, so this on the right side here is what we call as attribute rules. Means that what operation we want to do with the P, R, and S. So in this case, it says this code actually will do addition for R and S, and the value will be inserted into P, will be assigned to P. Okay. So what we can do is in the recursive descent, we create a method s, okay, void s. So in the bracket is a parameter, we call a mutable int p, which is the object that we created in the previous slide. Okay, so in the parameter is mutable p. So remember here, if you see in the grammar, s and then they have attribute p. So means that we create method s with parameter p. Okay, now we look into the right hand side. So we read the first terminal. If token.getClass equals to a, then get that token. Okay, read that token. Then you do method A. So do method A with a parameter R, and then you do B with parameter S. Okay, this is the information on attribute. Okay, and then what you do is you must indicate in your code what operation you want to do with that attribute. So in this case, I want to add R and S and assign it to P. So it means that all I do is P.set. So what I set inside P is get the value of R. So R.get plus S.get. So in this case, actually we want the value. Okay, so it means that here actually is R.value plus S.value. So we use the function get. Get here is to use to get the value of that particular object. Okay? So this is how you convert or you implement attributed grammar using a recursive descent. So attribute will be represented or implemented as a parameter, and then the rules also need to be inserted into your code as an operations after you have read the input. Okay, so that is why they said that attributed grammar is to indicate, to determine what would be the output of the program. If you see the grammar without the attributed attribute, with the attribute, it will only goes like this: S goes to A, then A, B. So without any meaning. So we only can look into the syntax error, whether it goes one after another or not, whether it can be instantiated correctly or not. But we doesn't know what this grammar is for example. So when you put attributed attribute, then you put the attribute rules, you know exactly, actually this grammar can be used to do additions. Okay, so that is why we say attribute grammar is to indicate the purpose of the code, which is also we call as semantic. So this is also called semantic function. Attribute grammar is a semantic function because you are giving meaning to the grammar. Now we go a bit further on the attributed translation grammar for expressions. Okay. So what does it mean? On the translation grammar, if you could remember, when we do a translation grammar, we talk about an action symbol. Okay, action symbol. So we want to know how we can use that in the attributed grammar. Okay, so the output of the translator will be a stream of atom. So what is atom? Atom is actually a statement. Okay, statement in your code. Okay, so we will look at how is it this atom. Okay, for example, in this case, I have an operation A plus B times C plus D. So the question will ask you what will be the output atoms of these particular operations. So output atoms is the operation you done in the computer system. So what actually happened in the computer system, including the memory allocations. So in this case, what you do first actually is the multiplication. So the code is mul B and C. So you multiply B and C and you store it inside T1. T1, T2, T3 is actually a temporary storage locations. Okay, or we use a stack. For example, maybe a temporary stacks. So this is to store intermediate result at the runtime. Okay, so after you have do multiplications, you do a summations of A with the one that you store in T1, which is T1 is the result of B times C. Okay, then the result you store in T2, and then you add whatever in T2 with D. So that is the step-by-step process. to calculate A plus B times C plus D. Okay. So this is the translator. Means that with this code, the translator should be able to produce these steps of process so that it can tell the system what to do first, what to do next, what will be the last. Okay, so that is a translator. So the output is a streams of atom. So this is a stream of atom. Okay, the one that are in the red rectangle here, streams of atom. Okay, so each atom, okay, each of the atoms. So here got 3 atoms, 1, 2, 3. In each atom, you must have operations. What you want to do, multiple, additions, divisions, okay, the operations, and then a left operand, okay, the one left operand, and the right operand, as well as the result. So the result will be stored in the temporary memory in this case. So this is about the streams of atom that translated from the expression that you give here. Okay, so the attributed translation grammar, so this is example. So how it looks like. For example, we look at grammar G21 here. Okay, if you can refer to this, actually is the expression that we have looked into in the previous video. So actually the operations will be represented as an action symbol here, in this case add, multiply, yeah, but with informations of attribute. This is the subscript down here, so it much more complicated, yeah, much more complicated and complex. So this is what we call as attributed translation grammar. It has attribute, it also has action symbol on what to do. Okay, so on the right side here shows the derivation tree for grammar G21. So this is a derivation tree is used to derive A plus B. Okay, so if you look here, you have the identifier A and also identifier B from the grammar you get. Okay, what we want to do is to do add operations. So in this case, you are informing the system to do addition. Okay, to do addition. So how? So you do A plus B and store it in T1. Okay, so this double derivation tree show all the representation you can get from grammar G21 for expression A plus B. How to translate the expressions with a recursive descent. So we want to know how to code it. For example, we get a rule number 1, expression P, term Q, Alice Q, P. So it's the same way. So any non-terminal will be a method. So here you have a method expressions with a parameter P. Okay, now you start to read your you call the object of mutable object, create the object. Okay, so the object is called Q in this case. So you read it. Okay, the left parenthesis or identifier or a token is a number. So any. Okay, you can read. The token can be any. Okay, is either left parenthesis, identifier, or a number. So next is the first you start with term Q. So term is a method, Q is a parameter, and ELIST you have as a method, and you get the value of Q and P as the parameter. Okay, so this Q actually is inherited from the one before this. Okay, all right, so this is how you write recursive descent for these particular rules. Okay, another example here to write this recursive descent for these rules number 2 and rules number 3. Okay, we start with ELIST. Okay, ELIST, and the parameter, there are 2 parameters here, P and Q. So you write integer P and a mutable integer Q. Okay, so this is the object reference. So and then you call the object and you get the class. This is to read the input. So the input will start with a plus sign. plus here, so token dot plus. So if it is token dot plus, then token dot get the input, and then you continue with term r. Okay, so term r is the parameter. Okay, then there is addition here. Okay, addition. So means that you need to actually to store the information inside S. So s.alloc means that the temporary storage. Okay, alloc means the temporary storage to store the value. Okay, now what will the atom is add B, R, and S. Okay, so you put out your atom. Okay, put out the atom add here. Okay, and then continue with the next method, a list, with a two parameter S and Q. Okay, so that is the end of rules 1. So for rules, for next rules is to read the token. So it should be n of the string, or the token is the right parenthesis. Okay, and then we said that Q, if you look into the rules here, it says that you put that Q dot set equals to P. It means that you assign the P value to Q, else it will reject. So that is under rules 3. Now we want to look into the expressions for a subset of a language. So here we want to see some important expressions that we normally use when we want to construct or develop our code. Okay. So there are a few, like in this slide, we have a level, jump, tst, and move. There are also Boolean expressions as well as assignment statement. Assignment statement expressions. So we will look one by one. The first one is LBN, JMP, and TST and move. So these are the atom that we normally use. Like for LBL is a label name. Okay, so the purpose here is to mark a spot to be used as a branch destinations. So LBL is used to mark what will be the destinations for that particular code. So normally we label it L1, L2, L3 as just a labeling. Okay, just a labeling. Jump, JMP, is also a label name. Okay, so it is used for unconditional branch to the label specified. So this is normally used when you have a while loop, for loop, and also the if statement. Okay, you need to indicate that if a certain condition is met, then you need to jump to maybe another level. Okay, so that is the purpose of jump. TST is used for comparison. When you have a Boolean expressions, you want to compare between two expressions, expression 1 and 2. And this also will branch to the label if the result is true. Okay, if the result is true, then you have to go to another level. So TST normally used when there is an expression to compare. Like in the if statement, they have a comparison for the expressions, then you need to use a TST. Okay, here is the example. Okay, let's say we have a if statement, if x equals to 3, and then the statement. So actually when you want to translate it into an atom, they need one atom called TST. Okay, means that if they do TST here, means that you are forcing it, the compiler, to check whether the condition here is true or false. Okay, so it will branch to the level only if x equals to 3 is false. Then only you give a level. If it's false, then go where? What will be the next operations? It's something like that. Okay. Another example here is while x greater than 2, then you run the statement. Okay. So for one statement, then you have to put the label first. Okay, you put the label. So you are in which level? let's say L1, normally start with L1. So then check the condition. If x greater than 2, you do TST, okay, to check whether the condition is true or false. Okay, so it here say branch to level 2 only if x equals to 2 is false. So it means that if this is false, what we do is to jump to the next operations, level 2. So level 2 normally will contain another operations. Okay, otherwise if it's true, then do the statement. Okay, then the statement, if the statement is done, then we need to jump. We need to indicate we want to jump it where. Maybe level 1, maybe level 2. Okay, normally while loop, we'll jump it back here. Okay. So here is the Boolean expressions that we use. So we have in this slide, we have the code for each of the comparison. If it is equal is 1, less than is 2, greater than is 3, less than and equal is 4, and so on. So we also represent the logical complement as well, okay, to indicate and the code as well. Okay, so this code is important when we want to write the attributed translation grammar. Okay, so the process of Boolean will, all we need to do is to put out the TST atom which allocates a new label. Okay, so the TST will check and allocate a new label after that operations and branch to the label when the comparison is false. Okay, so given this grammar, Boole expression a label. Okay, expression P compare C expression Q. So you need to do this is the action symbol is to compare. So action symbol, remember, it is force the compiler to actually to do the operations. Okay, so in this case is TST. So TST here will be P Q, which is you compare P and Q. Okay, then using what we call that is this Boolean expressions. Okay, T minus C and level. Okay, this T minus C actually here it is just a representation to show that actually this is can be replaced with this number, one of this number. Maybe 1, maybe 2, maybe 3. Okay, so 7 minus C, you can represent it with any number of code inside here. Depends on your programming purposes. Okay. Okay, next is assignment statement. So assignment statement normally is used to assign the value of the right operand to the variable on the left operand. Okay, normally you have P goes to Q. So what the assignment will do is just to actually assign it to this. The value Q into P means that you are moving the value of Q into P. So in this case, assignment statement that use move. Okay, it means that if you come across that particular operations, then you need to use move as your actions symbol. Okay, for example, in this case, you have expression P goes to assign expressions. So assign expression, then go identification equals to expression move, means that you are moving the value from the right operand to the left operand. So this is the summary overall of the attribute translation grammar example. Yeah, example for the CAF. So this CAF actually is the attribute translation grammar for addition, subtraction, multiplication, and divisions. So you can have a look one by one of these attribute translation grammar. So you will see the TST when they come with a Boolean expressions, they normally have TST because they want to compare two expressions. When they have assignment statement, normally they have a move operations, move atom, and then you have a add, sub, multiplications, divisions. Okay, for each of these operations of mathematical operations, we need to specify the temporary storage. Okay, temporary storage to temporarily store the runtime value, the operations at the runtime. Okay. Okay, now we can translate our control structure. Okay, so the control structure will be if, else, for, and while loop. Okay, so the important item here would be jump, tst, labels. Okay, so we are using this atom in order to translate our control structure. Okay, so why? Because our control structure normally have an operation such as unconditional jump, or go to, compare, or conditional jump. So this particular atom is important to indicate this process for a control structure. Okay, so in this case, as I said, the purpose of tst atom is to compare the value of expression 1, E1 and E2 using the specified comparison operator, which is compare. Okay, and then the branch to the label LBL if the comparison is true. So this is the comparison operator. So we have 6 comparison operator here. So this is the code 1, 2, 3, and 4, 5, 6. So how to write it? Then you have like tst a c and then a blank space 4. 4 will indicate actually you are doing this operation less than, means that you want to indicate whether a is less than or equals to c. That is what it means. Okay, so if you're given this particular atom, it would mean that you are actually comparing a and c. You want to check whether a is less than or equals to c or not, and then you go move to label L3. If it is yes, then move to label L3. So this is how you read the atom with the comparison operator. In this slide, we will see the control structure, the diagram, on how you can add the atom in between of the statement, control structure statement. Okay, what are the atoms that are required? Okay, for example, for this while loop, for the first statement, for the first rules here, statement goes to while Boolean expressions. So if you look into this flow chart, I think the flow diagram, yeah. So you start with while, you need to have a label first, okay, label, then you run the Boolean expressions, okay, run the Boolean expressions, and then if it's false, goes to another label, and if it is true, then you just go through the statement. Finish the first statement and then you jump back to level 1 until it is false. If it's false, then you go to level 2. Okay, so it also the same with for statement. For statement, you need to write for expression and then you write down what is the label. You start with what label and then read the Boolean expressions. If it's false, directly go to L2. If it's correct, then you need to go through the process down here. Okay, process down here, you need to jump to another level. So a lot more, because if you look into the for loop, the operations is much more complex compared to while loop. For if statement here, okay, we have an if statement, so we write down if, then the Boolean expressions is a level 1. If it is false, then you go to level 1. Okay, then if it is right, then you straight away do the statement and jump to level 2. Okay, so this is for if statement. If they have else part, okay, then do the else part. Yeah, and for the Boolean expression, they have several have more detailed process. Okay, more detailed process, which is they look into the expressions, compare with the next expression, and then do tst. Okay, and only then the process of identifying whether it's false or true will be determined. Let's look into the exercise. Okay, the question will ask, show the atom string which would be put out that corresponds to the following Java statement. Given this following Java statement, while x greater than 0, then statement. So how to write the atom for this statement? So for while loop, if you refer to the previous flow diagram, it starts with level. Okay, you write down what level first, and then you do an operations, okay, for the expression, which is a TST. Okay, so what you want to compare actually is between x and 0, and what operation is number 4, which is greater than, and then put it into and move to level 2, L2. Okay, branch to L2 if x is less or equals to 0. It means that if it is false. Okay, then you continue with the atom for the statement. Okay, depends on what statement inside this particular statement. Okay, so you write down atom for each of the statement inside the statement block, and then jump to L1. If it's done, then you jump back to L1. Okay, this is when it is false. When it is false, it goes to L2. Okay, this is how actually you put out the atom for this Java statement. Okay, given the Java statement, so this will be the atoms. Okay, so that's the end of the translating control structure subtopic. Okay, so next video we will look into chapter 5. So thank you everyone.